So, good morning again, everybody. Welcome for this new seminar from the Instituto Astrofísica de Andalucía. Today, we will have the talk by Gökhan Yücel from the University of Turkey, and he will talk about an unusual triple system CN line star. So, Gökhan Yücel is a postdoctoral research at the Department of Astronomy and Space Science at the Istanbul University in Turkey. Dr. Yücel completed his PhD at the Akdeniz University, focusing on the analysis of eclipse twin binary system. His research primarily revolves around stellar astrophysics, with a particular emphasis on spectral analysis and the study of solar-type twin binaries. So thank you very much, Gökhan, for being here. And the floor is yours.
Thank you very much, Emir. Hello, everyone. As Rene introduced, my name is Gökhan. Today, I will talk about our latest study, the triple system CN line. And I believe this is one of this kind in our galaxy, at least to our findings. So I would like to start with our where I'm from. Istanbul University. I mean, Istanbul is a great big city, most of you know. And our university is center of the old city, actually, the old Constantinople, let's say. It's center of it. And on the right side, our building on Istanbul University. The left side is this Bosphorus here. So I'm a member of Galactic Research Group. I joined 12 months ago. The basic of the main objective of this group is that the study of the evolution and dynamics and kinetics of our galaxy. How we do that? We look at the primarily for surveys like Gala, Gaia, SO, Apogee, etc. And what the study is mostly open clusters, field stars, and some CVs and binary stars. When I joined, I contributed binary star in this group. So we are almost 30 people. As you can see, we have 7 academics, 1 astronomer, 3 postdocs, 14 PhD candidates, and 2 graduate students. And one of the PhD candidates just last week got her PhD. So we have formally 4 postdoc researchers right now. So this is a picture of us from the last September. There was a National Astronomy Congress, and almost half of it's here. Hear me. So shall we start? I would like to talk about the history of the system, for example. It's first Morrissey in 2004 study of this system and showed that it's triple characteristic. That's it. They studied mainly to see the capabilities of Gaia spectrograph. As you know, Gaia spectrograph either 11,000 spectrograph on itself. Then specifically looks at the calcium lines here. And they try to do, if we study the binaries with this, with the Gaia spectral data. So they found the primary and secondary masses and radii and temperatures of these components, and they found that there's a third component, and it says significant light contribution, like almost 30%. And based on the fact that it's light contribution, they claim that this third component should be the similar mass of the other ones, but it should be more evolved than the primary and secondary. They found specifically they found the temperature of the system based on photometric calculations. So later on, Leo in 2021, they checked the minimum points and observed the system again and found the third components period, like it's almost 16 years. And based on as I mentioned before, the Marissa said that since light contribution close to third component mass should be similar to the other ones, they claim they analyzed the inclination of the third component as 25 degrees and found the third component eccentricity 0.38. And they also observed the system at phase 0.5, like the secondary in front of that, and took the spectra of the the star with LAMOS telescope with low 2500 resolution, and the analysis of the second component as the found the spectroscopically the temperature of this component as you can see here 6337 kelvins and metallicity of -6.67 index and log G as 4.37 CGS units. So why we study this system? As you know, the binaries are studied for a long time, but not all of them studied well studied specifically in today's capabilities. Now, most of the spectra of binaries can be now disentangled, and each component of spectra can be analyzed and found the chemical abundances, temperature spectroscopically more reliable than photometric observations. So, and as you can see here on the spectra, you can see the third component clearly. So there is no study on specifically on that. So we try to our main objective to find this third component parameters, fundamental parameters, and chemical abundances of the system. So what we so far. So as you know, there's a new telescope test. Primarily, its main goal to primarily find new exoplanets, but it's the work of it is also it's a good source for binary systems, existing binary systems, since basically same procedure is that. As you can see here, Parcos data, the previous studies used, and this is the test data. See, it's very perfect, almost perfect. And this is the normal time versus normal flat, and this is the phase. As you can see, it's very fine and good quality. So we can these old systems can be re-studied with this new test data and find the parameters more reliable, more accurate. So we using the test data minimum point, this one, we calculate this each time every point the minimum point of, and we do O minus C analysis, like find the minimum. And these points we added. These are the old Leo studies and the previous observation. These points, as you can see here, are test points. And we found we reanalyzed the period, and we found that actually the period is much smaller than the previous one. It was almost 16 years. This we found it's 8.6 years, and find the eccentricity as a little bit higher than 0.38 as 0.55. So we calculate orbits of the system. As you can see, this is the third component, and this is the closed binary system inside of it. As you can see, this closed binary if you think it's closed binary, a single star, we can calculate the spectroscopic orbit from the radial velocities and find find the spectroscopic orbit as this two star like. So we can calculate in mass ratio of two system. I mean, so here's the Balmer line. This is the angstrom. I forgot that's the X unit is angstrom. The Y unit is the normal flux. As you can see, we model spectra. Like we use Crookes model atmospheric codes and the spectrum for this one and scientific spectra. We built scientific spectra for each component based on previous studies, temperature and log G and metallicity. We recalculate the radial velocities for each component by that. But as you can see from previous this slide, that the closed binary has a difference with a different speed, like changing velocity. We need to eliminate that from the inner binaries components radial velocity, so we can calculate this orbit. We did that. As you can see, this is the third component, the black ones, radial velocity values, and the red one is this blues. I wish I could change the color so it's mixed up. Anyhow, we found the spectroscope orbits and find the mass ratio with inner binary and in the third component. So here the residuals. It's not so great, but it's very well for this kind of study. And this is the out of orbit. Like if you can this binary systems. here the spectroscopy parameters. See this systematic gamma velocity, like the center of the mass of the system, the outer binary and inner binaries together, and we find the system mass ratio third component with the inner binaries total mass 0.37 with a little bit high error. So we, as I mentioned, we calculate the inner binaries red velocities again with this extra velocity, and we fix the gamma corrected and recalculate. As see, there is not much difference, but we refined this parameter as you can see, the gamma almost 0, and our values so similar, but still a little bit difference. Then we solve this with new test data. As you can see here with the purpose, there's too much error in here, like you can see in the residuals here, and a test is almost 1 magnitude is better than purpose. We reanalyze the system inner binary. This is inner binaries radial velocities and test purpose light curves. We reanalyze this stuff and find the closed binary, like inner binaries parameters. As you can see, I'm not gonna waste time in it. This is the number you can see in the paper. Just to show that see the error are very low, very accurate calculations. So what we have done this there are two set of spectra in literature. One with Asiago spectra, one with Alloy spectra. We combine that. A total of 42 spectra is studied in the system, and we use Corel, the spectral descending code, which it works as it uses Fourier transformation to distinguish spectra. As you can see, this is the H alpha region. Okay. You can see the third binary, and this is the distinguishment. The top one, the black one, is the composite, like all of together. The red one is the primary, yellow one is the secondary, and the blue one and tertiary component. Third component. Did you see that difference? Like there is something going on here. The lines are too shallow for third binary. We checked that there is a problem. We thought we made a mistake. Like it shouldn't be like, since triple systems, we believe that have same origin of molecular class, so they have the same methods, the same abundances of. But we discussed that with the Professor Hadrava, who writes the Corel code, and say you are correct, your calculations is correct. So after that we analyze the chemical abundance of the elements and spectral analysis. We use SPA's code, the automatic code. We didn't use normally chemical abundance studies selected with higher resolution, with high signal ratio data, but our resolution is 17,000. Normally LOD has 40,000, but Asiago has 17,000. We need to degrade the resolution of LOD to 17,000 to start of descending. They need to have same resolution power, so we can do that. We lose the resolution, but we get signal to noise ratio a little bit higher than that. So as you can see here, also the red ones is the model for primary, so secondary, and the third one. These are residuals, and this is a specific region that's here, like here the zooming. You can see the individual lines here. As a result, we found each component's temperature and chemical abundances. As you may notice, the temperatures are close since they have the same light ratio. We expect the same temperature since light ratio based on star's luminosity based on its temperature and radius. So it's expected that. But I showed the red one. As you can see, there's a significant differences in metallicity. Iron abundance, as you can see here. We at first we thought there's something wrong. There shouldn't be like this difference. Like normally, you think that there's some error in disentangling or calculation, but we recheck for 5 times. These are results. So we thought that what could have happened in primary and secondary differences in there. I will talk about third component later on. There is a study on specific binary. I don't remember its name, but it says there shouldn't be this kind of difference, but it might have if the secondary or primary swallow a planet or around 15 to 50 Earth's mass, it can reach its atmosphere like 0.2 dex. It might be this cause this. We are not sure yet, but we believe that it might cause this. And third, as you can see, the tertiary component is way lower than the other one, way less abundance than the other one. But the other one, like alpha element, as you can see here, calcium, titanium, these are richer than iron abundance. And these are specific for hollow stars. Anyhow, this is all parameters for now. So how we calculate the third components radii? As I mentioned, we calculate light ratio since we know the temperature of the system, and light ratio is based on the components temperature and radii. And we calculate the radius of third component is 1.4. As you can see, we find the third component mass is 0.85. This is extremely old for this kind of stars. The solar 0.85 mass, if it was around this system, like H for we calculate the inner binary components is 4 billion years. If it was this H, it should be like not even 1.9 or something. But we calculate the evolutionary tracks. It's H 12.5 million years, billion years. Like it's almost the same age as our universe. And this is the typical age of hollow stars. And this is our second proof or findings, let me say. So we calculate its evolution. We use MESA code. If anyone knows the models for stellar astrophysics experiments, it's a very popular in evolution studies for stars at least. We find the initial orbit conditions. As I mentioned before, this system is 4 billion years and still have a very low eccentricity here, which means that this system still hasn't been circularized. So if we go back time and we can find the initial conditions, the initial orbital parameters like period and eccentricity for that. So we test with different periods with an orbital eccentricity start points, and we calculate the evolution and start the current orbital conditions, and find that it's extremely, as you can see here, initial orbital eccentricity is 0.98 and initial period 217 days. We have discussed about this with the reviewer, or he didn't believe that how can it be like so big and so extreme conditions to how can it be come to this site. But I showed that if the system has no eccentricity at first, the starting initial period would be like two days or something like that. And the system has the current orbital period is 1.96 days. And the eccentricity is that much difference in this kind of systems in evolution. Here in HDR diagrams, in HR diagrams, this four components, black one for primary, blue one secondary, and red one is tertiary. We calculate third binary as a single star, since it's almost no interaction with the inner binary. This left side, this left turn, I guess I should say, this indicates when the mass transfer starts in binary. This is not, there is no H in this graph, so it's not point great, but if you notice why it's changed to the left side, it takes mass from the primary in like 300 years, 3,100,000 years. So here, this is the orbital evolution, as you can see, H. See, it needs to start, the left side is orbital period, right side the eccentricity. See, it's the orbital period shrinking like immediately start to shrink, but later on the eccentricity only starts when the shrinking, start to shrink, it's shrinking around 50 days. See, only then the system is can be like that. So this is the current positions. B is when the B point, as you mentioned here, as you can see here, B is circulation orbit. Is 3.5, like almost 200 to 300 years. It will start orbital circulation, and the other points. I'm not gonna. I would like to waste time on here, to be honest. So you can read all. These are the all evolution calculation point, like important point, like when the primary core contraction starts at when what is the condition of primary and secondary components of the system when the primary core connection starts, and age of the system you can check it, and about how orbital parameters change. As starting of mass transfer starts at 4.435 million years, and then the orbital period drops to 1.66 days, and the primary drops to 5,000 Kelvin temperature, and secondary at the 6,200 Kelvin. And this is the HR diagram on the points where it's set. This F, I think the important one here is F point when the start of mass transfer, and the G. As you can see, when the start of mass transfer starts, the secondary component extremely gets hotter, and its luminosity increase. And at G point, you can see here the secondary is when the secondary enter the terminal H sequence, like when its hydrogen in its core it's depleted. So what we do, and as we need to check our results, to do that we use galactic code. I don't know if anyone knows that. It's a galaxy evolution code. We take this star and go back to time. Star in here, and before when it's entered the main sequence in here. As you can see, it's 14.5 kiloparsec, like age of the galaxy, our galaxy. And so it's as you remember, we found the minus 0.5 dex in metallicity, and this is the typical metallicity of these regions, minus 0.5 dex. And as you can see, is here the in galactic this revelation is here starts when it's born, and today it's near sun right now. It's the system is 300 parsec away from us, but it started from its evolution at minus 14.5 kiloparsec. And also we check the system stable or not. We use the Eggleton-Kissel as codes, formula at 1995. If the system, this calculations is bigger, smaller than 110.5, its system stable. As you can see, we found this calculation result 8.7. This system is very stable, very stable. And we also check if the galactic chemical plane, if the calculations are right, like chemical. We claim that the third component came from hollow, so it needs to be understood. Bansby in 2014, they studied all stars that know chemical abundances, and they catalog that. Its green points here is thin disk stars. The red one is the thick disk stars, and the blue ones, as you can see here, hollow stars. Here the definition of hollow, thin disk, and thick disk. As you can see, this minus is very around. This one for primary and secondary, and here primary and secondary. Is here, I don't know if you can see it, but this is primary and secondary, and this is the hollow. This is the third component, the tertiary component, third star. See, it's around hollow region, and again, it's very far from the others, the hollow region. We also confirm that this third component in the system came from hollow. There is no exact in science, but our findings indicate these results. So as a result, we updated its systems components in systems fundamental parameters. We find each component's chemical abundances, and show its evaluation, what they will happen in the systems. We confirmed also the system is hierarchical and stable, and also we found the birthplace of the this system's birthplace and conditions. And our findings are published in Astrophysical Journal. You can find here. It's very recent, actually. It's in January 15. They published. They accepted in December. And as so far, there is no system in like this. Like there is no capture scenarios. Always these scenarios, third system or fourth or both, they run away from the binaries or third multiple system. There is no in literature that the capture scenario is accepted. We are currently working on if this capture scenario is possible. Now, our findings indicates that, but we need to make sure that it's possible. So we are currently working on how star capture scenario could be happen. I mean, our findings indicate that, as you know, but there is no exact science, so we can't say exactly this. But our findings and our proofs or like that show that the third star in the system captured by captured by the inner system, near galactic edge of the galaxy or something like that. As here, I show that the movements in this inner binaries in galaxy. This is the edge of galaxy. Here are in this galactic center in this way. This is the portrait galaxy. As you can see, maybe they be captured around here. We believe that this, as you know, if you go to edge of the galaxy, the gravitational energies are very low since than inner galaxy sites or site. So as a result, thank you for inviting me here and present my results. And if you have any questions, I might take.
Hey, thank you very much. Any question for Gökhan?
I'm very well prepared for question because we have a very struggled review phase. So if you have any question.
I have one, just curiosity. How can you distinguish or difference if you only have test data, for instance, you only have photometry, how you can say that you are dealing with a double or triple star system instead of a exoplanet? Or you need the previous spectral information to say this, because only with the photometry you can say that.
No, because we can see the third component in the here spectra strictly. This image taken from Maris's studies. Okay. This is the primary, the right side, left side on the secondary, and the middle one is the tertiary component.
So without this, you can't say nothing.
No. We need to see. We need to see, or we can say actually, if you, for example, this minus C, we can say that if there is a change in minus, but as you can see, this observations like almost 35 years. But we need to kind of shape that if there is a system, if the third binary or fourth binary, or I mean third component or fourth component or double binaries or something like that, we need to see that this O minus C analysis. Or there are studies in new that the quadruple system, sextuple system like we need to see that here. We can see only here we only see the one and secondary is eclipsing. We can't see the third. Like for example, those kind of studies we see the multiple here eclipsing, multiple like shallower than the others one, but we can see that. There are a lot of studies right now, and also there are claims that the most binaries has a distant binary. Like these are quadruple systems actually. There are kind of studies that. But we are sure that in here, like for example, we can see the third component in here again. This image you can't see, like there is no such, like there are systems like that in spectroscopy. You can see the third component. But these are very rare, like very rare stars. Like the comprehensive analysis, like on the third component in triple system, is very rare. Or it may be visual system, visual. Maybe you can see that like that. There are a lot of studies about by Tocqueville around this system, the third binaries, and mostly the third binary, triple systems has a period like third components period, like over 400 days. There are study Kyle Conroy they studied the Kepler data. Most third components has a period of 400 days and 1200 days between that. But as they claim here, this is the it didn't formed in the same molecular, but it's captured. So this kind of state, and also the known shortest period of third component is 36 days. It just published in December or November in again astronomical, the shortest period of third component in a triple system. So I hope I can answer your question. So anyone else?
More questions? I have one. At some point, if I misunderstood, but you mentioned that the metallicity
Yes.
of the first and second component could be influenced by a.
Yes, according to this data, according to our findings, there is a difference. There should be like this much difference. There could be differences, but not this much.
So could be some planet that
go
inside.
There is a study in here. I didn't put here to not too much dissolve presentation, but there's a study in the paper. There is a citation on that paper. Also, you can read that from that. I mean, this is a strong claim. This probably like our data is not so great. As you can see, signal ratio is 82 for primary, secondary for 75. This is after descending. Normal descending procedure increase the signal ratio. We use 42 spectra for this system, but still it's not enough. Normally, chemical abundance studies minimum it's hundreds. They expect to study at hundreds. So probably there are mistakes, but this much difference is not can be explained with the procedure error or something like that.
I mean, the error in the metallicity is
really
it's low.
not so realistic, to be honest. It's very low. Yeah, very low for this kind of signal to ratio. But this is our automated system, so they found the solution in a space like phase space. So they are automated calculations.
The only metallicity that indicate that is iron, and the others
magnesium
are really similar.
Yeah.
So
we expect that it's maybe
it's a big ball of iron.
No, not iron. The rocky planets like 15 to 50 mass Earth mass planets. Maybe it can be slowed. It can be solved by the secondary.
Well, okay.
I mean, we're not sure. We just can. It can be because there is a study of kind of this and explains that must be a reason.
And this is assuming that the primary and secondary they form
in the same molecular class.
Right.
But I'm not sure what I'm going to say. But I believe that multiple exoplanets are formed generally in multiple star system more because there is a lot of perturbation.
Right.
So there is a lot of gravitational effect. More common to, but they can be swallowed. Like there was a study actually. I should have looked at that. There was a study like that. The binaries, the planet eaters or something like that. That was the title. I should have checked, but this is not uncommon. I think.
Nice contamination.
Yeah.
Okay, people in Zoom, if you want to ask some questions, just raise your hand. Any other question here in the room?
In more view, do you have something there?
Yeah, more. Oh, you mean?
Thanks for the talk. This is a very complex modeling work. I have a couple of questions. How did you take into account the multiplicity of your system in the MESA modeling?
I should talk to the camera. We only inner binary. We use binary. What can I say? Binary module for inner binary, and the third component only calculate as a single star. We calculate like that. We didn't. There is no solution for triple system in MESA. There is no calculation, evolution calculation for MESA right now. Maybe they plan to further, but right now we can only calculate binary evolution, its orbital condition, and also in itself evolution, like stars itself also evolves, and single stars.
So there is more. That's the binary. Okay, maybe, yeah.
I can't.
Yeah,
Can I-
maybe you answer all the other questions. Does the binary model of MESA work for triples, or did you model the star
No, not right now. Not
as
right now.
singles? Right.
Now, maybe you can work it like as we calculated here, the stars, like here, I showed that. If we think that the inner binary is a single star and the third binary is a single star, you can maybe make a calculation for that, but this is the period is too large for find a meaningful solution.
Okay, he said perfectly exactly what I wanted to know. Thank you. More questions, more comments on the chat or here in the room? Okay.
I strongly recommend to read the paper. There's more explanation, more. I don't want to bother you with the details, so I just want to point out the important points. I would really recommend you read the paper.
Okay. Okay, so thank you again. He will stay here for this week, right?
Yeah, I will be here all week. Okay. And Monday I will. I have the
Come back on Monday. Okay.
Yeah.
Thank you very much.
Okay.